Hi, everyone. So I wanted to talk a little bit about not just, I think there's been a lot of like really phenomenal work that's been done on, renewables and PPA and kind of how to quantify that. And I wanted to talk a little bit more about flexibility of the demand specifically. So the basic rule of the grid, right, is for every second, electricity supply has to equal electricity demands plus whatever losses you have on the lines, right? And whatever losses you have on the lines actually, closer, and whatever losses you have on the lines actually varies with temperatures and with the load on it, right? So that's actually not a constant. And so what used to happen is we thought of demand as very, very static and supply as dispatchable. So when you flip the light switch, there was a power plant somewhere that would spin up. And now, we can actually control our demand much more dynamically. Okay, so let me run really quickly through how the electric grid is designed. This is specifically on what's called deregulated markets. It is a misnomer. Everybody is regulated. Utilities are regulated. The grid operators are regulated, but some a little bit more than others. And these are the ones that have auctions, so they're a little bit more transparent compared to what we see in like fully integrated utilities. Okay, so you've got a grid operator, right? So this is true for about half of the areas in the US and for a lot of Europe. So day ahead, they predict the demand in a variety of basically all of the places that they control, right? Then solve what's called the optimal power flow problem. That basically means demand and supply matching given the constraints. And then there's an auction for supply, right? So a lot of renewables bid in at zero, but as the auction stacks up, the end, right, like when you've met the demand, that's what everybody else gets paid. Similarly, an hour ahead, right, you have better prediction demands, right, because a day ahead, there's still a lot of errors come from, let's say, weather forecasts. An hour ahead, you have a slightly better idea of what's going on. You don't have quite enough compute time to solve the optimal power flow problem, so you solve a weird twist on that. And then there's auctions for supply, both straight from the grid operator, but also from anybody that committed to day ahead that can't meet that demand. And then there's a bunch of real-time things, right? Like frequency in the grid can't vary by more than like 0.1 hertz. And so, you're looking at very fine-tuned, I see a smirk there. So you see there's not necessarily a great reason as to why that limit exists. And so, you kind of need to fine-tune that. And then, of course, there's things like, hey, a power plant went down, there's some emergency. They literally have the ability of shutting off neighborhoods and cities. Not used very frequently. Okay, so what does that demand look like? Here's an example of, this is specifically the California grid operator. When you have 40 million people, you can do a much better job at predicting the demand closer. The fewer people you have, the harder this gets. So the dotted green line is a day ahead, the dotted black line is an hour ahead, and the solid green is what actually happened. So you can see this particular day was pretty close. Also, we're saying that the congestion really, really matters. This is 6 p.m. in California, which is one of the highest usage hours. And you can see that in the blue, you've got some negative prices, and in the red, you've got some really high prices. So here's a giant, giant spread. So where you locate your industrial facility, matters not just which grid you're at, but also where exactly you are on that grid, especially if you're exposed to real-time prices. Okay, so now the job of a utility: maintain the poles and wires, buy some power, sell some power, basically, and a couple of other things. Specifically, they really want to protect residential consumers from real-time price fluctuations, because those can be wild, right? Like electricity can cost 10, 15 times more one hour than the next, and you don't want to expose the average grandma to this because there's no way of for them to even know what that is, let alone react to it, right? But you do want to be exposing industrial customers, right? Which is, I think, what at least some of the folks in the room run large data centers. So you do want to expose industrial customers to anything that they're doing on the grid that makes the utility or the grid operator's job more difficult or more expensive. For example, if you have large power spikes, right? So for example, here's what's called the demand charges, which is part of every industrial, or almost every industrial operator that I know of, right, which has the 15 minutes in a month that you use the most electricity, that sets what's called your demand charges, right? So that basically means this is the the utility has to assume that you can use that much at any time you want, and so they have to upgrade the lines, the transformers, all of the electrical infrastructure up. So if you cut that down, right, if you make sure with your flexibility that you don't have these spikes, not only are you reducing your bill, you're also making the job of the utility a lot easier, right? And so there's kind of you don't have to upgrade some of that infrastructure. Okay, so, no, given that, right, like what are things that you can do that would be, would really help the grid operate? Okay, so one thing that's important to know is kind of what flexibility you have. And of course, what flexibility you have depends on, how much you have to run your equipment and still, and can still generate revenue. And that will, of course, vary by the price of electricity. So let's say if, 2 cents a kilowatt hour, maybe like the cheapest solar in the world, basically, if you can run at 30%, you can literally just co-locate with that solar farm. In that case, of course, that's very likely to be older hardware, right? The hardware is expensive. And so when you're using expensive hardware, you typically have to run it a lot more in order to just be able to pay back those costs, right? So this is just one example, but the idea is, what is the flexibility? Like, how much can you actually give up in order to participate in these variety of grid programs, right? So if we're the idea is that a lot of people are already using PPAs to bring in lower emissions, lower cost electricity onto the grid. But the problem of balancing, like the hard problem of what you do with the intermittency, is now generally pushed to the grid, right? Whereas here, you can use your flexibility to help that integrate. Okay, so let's say you've got extra 3% of flexibility you're willing to give up, right? You're willing to shut down for 3% of the time, right? There are a bunch of demand response programs, meaning the hottest days of the year that most expensive, dirtiest electricity, you can help not have that. And so you basically sign up. It's usually no more than 10 days in the year and usually just a few hours a day, right, that you would shut down. And for that time, even if you're never being called on to do that, just you providing that flexibility to be there if it's even needed, it might not be needed, like there's like a monetary reward for it, and also you're like really helping the grid. It really depends on how predictable your baseline is. When I messed around with this back when I was working in Google, nobody would come in on Fridays, and so Fridays were lower. Like even if you did nothing, it was lower than your baseline. Baseline is usually 5 business days out of 5, and so there's a little bit of caveats there around what you do there. Okay, so let's say you've got 5%. You can probably reduce those demand charges, so those big spikes that make the utilities upgrade their transformers and their wires. That's something that you can probably reduce. You can also maybe do this with batteries or solar. If your compute is like very constant and really the spikes are basically caused by AC, those could coincide with solar time. So there might be other ways of reducing that rather than directly flexibility. Okay, so this is when it gets interesting. You've got a little bit more flexibility. One thing you can do is get exposed to real-time prices, right? So essentially, instead of the utility buying and selling power on your behalf, you can say, well, wait, I can do this better because I can predict my demand better, and because if prices get really expensive, I can shut down, right? So if you have systems, right, this is of course a lot of work, but if you have systems that can plug into the signals from the grid operators, and they can shut down your systems for the hour that it's really expensive, you can do a much better job than the utility, and so that would be both cheaper for you and cleaner for the grid, right? And there's kind of a big question of whether the price signals are related to emissions, right? Which I think so it depends, right? If you're in Europe and the US, you can use watt time to find out whether that's true or not and make decisions based on both. But otherwise, like even if you don't, right, if you think of even natural gas, combined cycle natural gas is 60% thermally efficient, right? Peakers are, I don't know, like 40% best case scenario. So even for the same amount of natural gas you burn, you get 1.5 times more electricity for the steady sources rather than the spiky sources because of the better heat recovery, right? And so like even there, I think that makes sense. If you have that kind of flexibility, one of the other things you can do is stranded sources, right? So, there's been a lot of talk recently about like using oil and gas flares, right, to power Bitcoin miner, which I think makes like tons and tons of sense. But, keep in mind, in the US, at least they move every 6 months. You're running your own generator, so you are going to have a lot more downtime than the like 99.99% uptime of the grid. I probably forgot a few nines. Okay, so then if you have really, really, really a lot of flexibility, right? If on, obviously for at, 70% flexibility, you're willing to give up, probably you're going for like 2-cent electricity or something very cheap with like older hardware. And by the way, older hardware has the upside of having better embodied carbon footprint, right? Because you're reusing stuff for longer. But in that case, literally you might as well just plug right into a renewable energy farm and just like disconnect the grid entirely. Because if you can match your demand to the supply of renewables and you're on the grid, you're still like contributing to congestion on the transmission lines, right? So you're not actually totally neutral in that case. But if you collocate right next to the producer, then the entire grid system is kind of out of it, and none of that maintenance and the congestions and the loss of electricity to everyone else because of the large stuff that you're pushing and pulling, like none of that is there. And, that should reflect in the pricing as well, right? Or you can build your own renewables and then plug into those. Okay, one last thing is if you have fine-grained control over your electricity, right? If you can do it at a 4-second basis, right? If you can kind of like up and down your electricity, then you can help with frequency regulation. That is extremely valuable to the grid, right? Because there's not that many things on it right now that can do that, and they can be metered, right? EVs are probably a really good use case for it, but they require a special expensive meter, so you would never do this for one EV. You'd only do it for a fleet. So that's something that could be like a very, very lucrative market. And of course, if you can do it on a 1-hour basis, then all of the real-time exposure makes a lot of sense all of a sudden. Okay, so the 3 things that I think make sense to think about is picking the right location in the right grid. And that depends on your flexibility. So for example, you could go and let's say you have 20% flexibility. So you look at the LMPs, the local marginal prices at the area you're interested in, and add them all up to 80% of the cheapest stuff and see where that is the cheapest, right? Which may or may not coincide with where it's the cleanest, right? But I think Watt Time can help you do that. Cut your demand at like really, really strategic times, right? And even as low as 3% demand flexibility can get you quite a bit. And then consider stranded energy sources. And for all of these things, I think there's like really cool tools that we can build to make it easier for people to integrate into that. Yeah, I think that's all I got. Thank you.